In this video, we'll discuss variational inference, which is a general set of methods to approximate intractable distributions in machine learning in general, but also in particular to approximate the posterior distribution of the weights in a Bayesian neural network. Variational inference is a broad field of research, but in this short video, I hope to be able to provide a good overview. Let's dive right in. Variational inference. The goal of variational inference is to approximate an intractable posterior distribution, P of the parameters theta, given the data D, by a simpler distribution, which we're going to denote as Q sub phi of theta. So this is some distribution Q that is parameterized by this phi. And we're trying to change these parameters phi in order to make this distribution similar to that distribution. So the approach here is to pick some model family, and we have freedom in which model family we pick, for example, a Gaussian, that is parameterized by this phi, and then optimize these parameters phi to make Q sub phi as close as possible to the posterior P of theta given D. Now, in order to make the two as close as possible, we somehow need to quantify how different they are. And unfortunately, since this posterior distribution is intractable, we can't evaluate it. And so we also can't evaluate any measures of distance, such as this KL divergence that we frequently use in order to measure the distance of two distributions. But fortunately, as we will see, we can actually still implicitly minimize this KL divergence here by rewriting this KL divergence as different terms. This goes as follows. The KL divergence between two distributions, here this Q distribution and this posterior distribution, is the integral of the first of the distributions times log of the first of the distributions divided by the second distribution. And so here we just wrote out that definition for Q sub phi and the posterior as those two distributions. We can also write this integral as the expectation of this log here with respect to the distribution Q. That's nothing else but the definition of this integral is just an expectation over all the possible values of theta with respect to theta coming from this distribution Q. Then what we're going to do is to apply Bayes' rule to this posterior here, rewriting it as the likelihood times the prior divided by the marginal likelihood or evidence. And then what we do is to apply the facts that, well, log of A divided by B is log of A minus log B, and log of A times B is log of A plus log of B. And so we basically collect terms here. We have here a log of this term divided by these terms. So that's this A and this B. So we have this term in the positive and these two terms in the negative. And then we multiply this here by P of D. So we have another additive factor of log of P of D here. In the next step, we notice that this log evidence term here doesn't actually depend on theta. So we can actually take it outside of this expectation. Notice that these parentheses is here and this parenthesis is here. So we took this outside of the expectation because it just doesn't depend on the theta. And that is a very critical point here because this log evidence, that's actually a term that we also can't compute. This is intractable, but as it turns out, it actually doesn't depend on the theta, so we actually don't care about it. It just becomes a additive constant. And then finally, the last step is actually quite simple. Here these two lines are identical. It's just that we added color here. So we have these two blue terms here combine in order to make this new KL divergence here. And that's, again, a KL divergence. This was a KL divergence, but the two are very different. Down here, we just have the prior P of theta, whereas up here, we had the posterior P of theta given the data. And the prior, that's actually a relatively simple term. We can compute that, and we can actually compute the KL divergence between this prior and our Q distribution. Whereas this posterior up here, well, that was the mean thing that is intractable and that we actually can't compute. So we are replacing one intractable KL divergence by the tractable KL divergence and some other terms. So namely this red term here, well, we just leave here. And well, of course, we also still have an expectation coming from here over the Q distribution of this probability of the data under the parameter theta. And then we still have this log evidence here. Okay, so this is exactly the equation we derived on the last slide in a nutshell. We had this intractable KL divergence, and we rewrote it as this tractable KL divergence minus the probability of the data under this Q distribution, plus an intractable constant. And what we're now going to do is to take these two tractable terms, and we're actually going to move it to the other side of the equality. And that only leaves this constant log evidence on the right side. And since this log evidence is just a constant, we can now realize that we can implicitly minimize this KL divergence by maximizing this part here. And those two terms here, they also have a special name. They're called the evidence lower bound, ELBO. So recall that our overall goal was to minimize this KL divergence here. And we implicitly achieve that by maximizing this evidence lower bound. Let's have another closer look at this ELBO and the terms in it. So the ELBO embodies a trade-off between fitting the data on the one hand, but also being close to the prior on the other hand. So this red term here, exactly this red term up there, this is the expectation of the log probability of the data for models phi sampled from this Q distribution. And we want to maximize that. We want to make the data as likely as possible under the Q distribution. And this blue term here, also the same as the blue term up there, that is the difference of our Q distribution from the prior. And we want to minimize this one. And that's why there is this minus here. So why is this called the evidence lower bound? Well, so we know that the term here on the right is the log evidence, the log marginal likelihood. Those are equivalent terms. And this is a constant. It doesn't depend on our choice of parameters theta. And we know that this KL divergence here is greater equal 0, because the KL divergence is always greater equal 0. It can't be negative, which means that this part here this elbow has to be smaller equal to the right side. So it is smaller equal to the log evidence, and that's why it's called the evidence lower bound. It's a lower bound on the log evidence. And the nice thing is that for an appropriate choice of Q, such as, for example, a Gaussian, this elbow is tractable to compute because we can compute the log probability of the data under Q, and we can compute the KL divergence between Q and the prior. And so if we can compute the elbow, then we can maximize the elbow. If we do that just by gradient-based computation, standard SGD, and maximizing the elbow then implicitly minimizes the KL divergence because the term on the right stays constant. So if this goes up, this has to go down. And minimizing this KL divergence is what we set out to do because we want our simple distribution Q to be similar to our intractable posterior distribution P of theta given the data. And when we have achieved that, when this Q is very similar, in the extreme when the KL is going towards 0, then we can simply go and replace every occurrence of this posterior by our simple variational distribution Q. And for example, in the context of Bayesian neural networks, we then have a tractable distribution for the posterior, and we can sample from that. And then we can get nice, proper uncertainty estimates for neural networks. Okay, so variational inference is a very active field of research. We just saw the elbow approach, and this is very popular inside of variational inference because it allows us to approximate this true and tractable posterior with the simple variational posterior, and therefore replaces this difficult integral. And this approach also has a wide range of different applications. In particular, you actually saw this last week in the context of the variational autoencoder. There we used exactly the same elbow trick in order to do variational inference in the variational autoencoder. But there's also a lot of other ongoing research on variational inference that I can't discuss in this short overview video. But let me give you a quick summary of two main directions. So one issue of elbow is that it requires calculations over the whole data set because there is this log likelihood term of the entire data in there. And you can circumvent that by also doing Monte Carlo estimates, very similar to what we used to do with mini batches in SGD. And then there is actually various methods for actually reducing the variance in the resulting gradients. We have variance in the resulting gradients of mini batches, and there would also be variance in the stochastic variational inference, and you try to reduce this variance as much as possible. And the second line of work that I briefly want to mention here is that, well, the choice of Q is actually really important. So you need to trade off the expressive power on the one hand against the computational feasibility in terms of the memory costs and the speed on the other hand. And the holy grail that people are working towards is to come up with a formulation and a type of Q that allows us to basically use a standard optimizer, such as SGD or Atom, and that doesn't have any overhead, but that directly gives us uncertainty estimates for free. So we can look forward to interesting developments in this field in the future. All right, that brings us to the end of this video. And as always, I'd like to leave you with some questions. So I encourage you to pause the video here and think about them to activate the material. Thank you, and I'll see you in the next video.